Have you ever built a model that seems to perform perfectly on the data you used to teach it, only to completely fall apart when faced with new, unseen information? It is a common challenge in machine learning, and understanding why it happens begins with how you interpret your training and test set results. Interpreting training and test set results is fundamentally about understanding how well your machine learning model generalizes, meaning its ability to perform accurately on new, unobserved data. By comparing the performance metrics, such as accuracy or error rates, from your model on both the training data and a separate, independent test set, you can diagnose whether your model is learning effectively or encountering issues like overfitting or underfitting. The core reason we analyze these two sets separately is to ensure that our model has truly learned the underlying patterns in the data, rather than simply memorizing the training examples. A model that performs exceptionally well on the training set but poorly on the test set is likely overfitting. This means it has captured noise and specific details from the training data that do not generalize to new data. Conversely, if a model performs poorly on both the training and test sets, it is typically underfitting, indicating it has not learned the fundamental relationships well enough to even perform adequately on the data it was trained on. To practically interpret these results, look for key patterns. If your training accuracy is high and your test accuracy is significantly lower, you have a clear sign of overfitting. This gap suggests your model is too complex for the given data, or it has been trained for too long. If both training and test accuracies are low, your model is underfitting, possibly due to being too simple, not having enough relevant features, or insufficient training. The ideal scenario is when both accuracies are high and very close to each other, which indicates a well-generalized model that has learned the task effectively without memorizing. An important nuance to consider is the risk of data leakage, where information from the test set inadvertently seeps into the training process, leading to an overly optimistic assessment of model performance. Another advanced technique for more robust evaluation is cross-validation, which involves partitioning the data into multiple training and validation folds to get a more reliable estimate of generalization error. These approaches help you avoid common pitfalls and ensure your interpretation is as accurate as possible. Ultimately, the careful interpretation of training and test set results guides you in building more robust and reliable machine learning models. It helps you identify when to simplify your model, gather more data, or adjust your features, ensuring that your final model performs consistently and effectively in real-world applications where new data is always the ultimate test.